Today we're talking about related rates day two. Day two is it's going to be very similar setup, but we're adding in a little extra step where sometimes in certain situations, before we actually solve out the equation, we might want to eliminate one of the variables before we derive it. And the reason why would be because that variable isn't actually changing, one, or two, I don't have enough information, so I need to get rid of some variables. So I use a ratio to replace a variable with another one. We'll see it here in a little bit more, but let's talk through our steps again. So first step, of course, is to draw our diagram. And then this time we are also adding in that first step of Fuigi. Okay. Then our second step is that using that ratio, we're going to solve one variable in terms of another. And we're going to see that here in our first example, number 8. And then number 3, we're going to substitute anything we need to into our equation E and then differentiate. And then step 4, of course, plug in our given when into our equation and solve for the find, whatever we're trying to look for. Okay, so let's look at 8. So 8, an inverted cone, has a height of 9 centimeters and a diameter of 6 centimeters. It is leaking water at the rate of 1 centimeter cubed per minute. Find the rate at which the water level is dropping when H is equal to 3 centimeters. Okay. So let's draw our picture first. So we have an inverted cone. That is leaking water at a rate of 1 centimeter cubed per minute. It has a height of 9 centimeters, so height here is 9 centimeters. And it has a diameter of 6 centimeters. And I want to find the rate at which the water level is dropping when H is equal to 3 centimeters. Specifically. Okay, so there is our nice little picture. So step 2, we're going to fill out our Fuigi. So what do we want to find? The rate at which the water level, so water level is the height of the water. So I want to find my dH dt. When do I want to find it? I specifically want to find it when H is equal to 3 centimeters. Okay, given information. Okay, my given, I was told that normally the height is 9 centimeters when the diameter is equal to 6 centimeters. Okay, and just because I think we're going to need it for our equation, if the diameter is 6 centimeters, that would make the radius equal to 3 centimeters. Okay. Other things we're given, this 1 centimeter cubed per minute, centimeters cubed, okay, that's definitely going to be a volume measure, and it's per minute, so it's definitely a rate. Okay, so it's a water leaking, so it would be the rate of change of the volume. So dV dt is equal to negative 1 centimeters cubed per minute. And last but not least, we need our equation, which is 1/3 pi r squared h for our equation of volume. Okay. So we have our diagram, we have our Fuigi. Okay. The second thing we need to do is we need to find a ratio to plug something in. And the reason why I know this, you can read through the problem. So we're told a lot about the height. We have a rate of change of volume, and we want to find rate of change of the height. But there's one specific variable you should see in here that we didn't find the rate of change of, or we're not told to find it, we're not given any information about it, and that's the rate of change of the radius. So if I'm not actually given a value for the rate of change of the radius, then if I derive r, because our radius is changing, but if I were to derive that r, I'd get dr dt, and then I'd have an unknown that I can't plug in for. So I can't end up with two unknowns in my problem. So what I have to do is I have to eliminate r from my equation by plugging in what it's equivalent to. Okay, and I can use some of the other information that they gave us. So the other information they gave us is that at the very start, okay, our diameter is 6 when our height is 9. Okay, which also means our height is 9 when our radius is 3. So that means our height is always equal to 3 times the radius, okay? Because that same ratio should hold true anywhere in our cone, okay? So then if I want to be able to plug in for r, I need this to just equal r. So that means h divided by 3 would be equal to our radius. So at any time in the problem, if I divide my height by 3, I should get the radius, okay? So now I can take this and substitute it in for r in my equation before we derive it. So step 3, we're going to substitute anything in we need to before we derive. So volume is equal to 1/3 pi, and then instead of r squared, h over 3 squared times h. So simplifying just a bit before we take our derivative, volume is equal to 1/3 pi h squared over 9 h, which we can simplify that all to be 1/27 pi h cubed. Okay, so that's our new simpler equation. Okay, now I can take my derivative. So the nice thing about eliminating one of our variables is now it becomes an easier derivative because I don't have to do the product rule when I derive volume. Now I'm just going to do the power rule with all those constants in front. So dv dt is equal to, that 3 would come down, so 3/27 pi h squared dh dt, which means our equation is just dv dt is equal to 1/9 pi h squared dh dt. All right, and last but not least, step 4, I just got to plug in everything I know and solve for what I don't know. So step 4, dv dt is -1. So -1, let me try it. -1 is equal to 1/9 pi, h is equal to 3, so 3 squared, and then dh dt is the one thing I don't know. Okay, so -1 equals 1/9 pi times 9 dh dt, which just means -1 is equal to pi dh dt, which means -1 over pi is equal to dh dt. And then I do need to add in some units, so it's the rate the height is changing. Height is just measured in centimeters, so this would just be centimeters per minute. And that would be it. So the key thing with today's related rates, y'all, is it's not anything too crazy. No, we're not really reinventing the wheel. It's just that little extra step. So yesterday's, sometimes we had to plug in something that's remaining constant into the equation so that when we derived it, it would just go away because that thing is constant, we're not going to get a derivative, a rate of change from it. Today, what we're seeing is sometimes we don't want a rate of change from everything in the problem because I just don't have enough information to solve the problem if I got a rate of change for everything. So instead, I can eliminate a variable. Same thing, I'm doing something before we take that derivative, so then I end up with fewer rates of change and, in a lot of cases, an easier derivative to take. Okay, so let's look at number 9. A spy tracks a rocket through a telescope to determine its velocity. The rocket is traveling vertically from a launching pad located 10 kilometers away. At a certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3 and is changing at a rate of 1 radians per 2 minutes. What is the rocket's velocity at that moment? All right. So let's draw our picture of our nice little spy rocket and our regular rocket and our spy. So we got our spy. Let's say he's got like a telescope. Okay. Over here, we got our launching pad with our rocket. Please do not judge my drawing skills. Okay. Some information they gave us. They said the rocket is traveling vertically from a launching pad located 10 kilometers away. This is 10 kilometers. At a certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3. So this angle right here is equal to pi over 3. And the angle is changing at a rate of 1/2 radians per minute. Okay. What is the rocket's velocity at that moment? Okay. So some key things to keep in mind for rocket's velocity, which line of this, hopefully you picked up on it already, but of this right triangle is the line that represents the rocket's velocity. Well, it's going to be our vertical line because it's the line the rocket is traveling against. So this is what I want to know, is this line right here, what rate is it changing at? Okay. So I have an angle, I have a side, and I have another side. So relating two sides and an angle together in a right triangle, this is going to be SOHCAHTOA, so sine, cosine, tangent, instead of Pythagorean theorem. Okay, so it's always key to understand what information do you have and what equation relates that information together. Okay, so step 2, let's get fwiggy with it. I know you're going to just love hearing me say that in class. Okay, so first off, what are we trying to find? Well, we're trying to find the rocket's velocity. So let's go ahead and give our side some names. I'm going to say X and Y. I think that's fair. Okay, and then of course we do have theta here. Okay, so I want to find the rate of change of y, so dy dt. Okay, when am I trying to find it? Okay, let's see. At a certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3. So I'm going to go with that's my when. Okay, theta equals pi over 3. Okay, other given information that we have. Okay, we also know that d theta dt, the rate the angle is changing, is equal to 1/2 radians per minute. Okay, any other information we have? Oh, we know x is equal to 10 kilometers. If we wanted to, we could solve for y, but let's hold off here just a bit because for all we know, we could end up not having to solve for y. Okay, so don't do more work than you have to if you don't have to. Okay, and then last but not least, we do need an equation. Okay, so what equation relates two sides and an angle together? Well, there's 3 different SOHCAHTOAs, but specifically, I'm relating my opposite side to my angle and my adjacent side. So which equation relates opposite and adjacent? Well, that would be tangent for tangent OA, SOHCAHTOA, O and A. So I would want tan theta is equal to opposite over adjacent. So in the context of my problem, y divided by x. Okay. Now for this one, do I have any, before I solve out, before I take my derivative, do I have any variables I need to replace or ratios like variables I need to replace with the ratio or anything remaining constant before I take my derivative. Let's see. I want to know about y. X, is that 10 kilometers between where the spy is set up and where the rocket is ever going to change? No, he's not like running after the rocket as he goes, okay? So X is never going to change. Theta is definitely changing. They gave us a rate of change. So if I get rid of X, I'll only have theta and Y. I have rates of change for both of those. So I think we should be good. So for step 3, the only thing we need to make sure we do before we derive is we need to plug in for X. So tan of theta is equal to Y over 10. Okay, and I'm just going to change this to make it a little bit easier to see that derivative to be 1/10 y. Okay, so now I'm deriving both. So the derivative of tangent theta is secant of theta times d theta dt. Remember, all of our trigs are technically chain rules. So when I derive the inside of my trig function, the inside of theta, I multiply by that derivative of the inside, I get d theta dt. And that would be equal to 1/10 stays 1/10. Y just becomes dy dt. So see how we don't actually have any of our sides in our problem now? That's why I said we can probably hold off in needing y, because we don't necessarily need y. Okay. So step 4, we just need to plug in everything we know and solve for what we don't know. So we don't know dy dt, so we're plugging everything in over on the left. So that's secant squared of pi over 3 times 1/2 equals 1/10 dy dt. Okay. So secant of pi over 3 is the reciprocal of cosine. Cosine of pi over 3 is 1/2. So secant of pi over 3 would be 2. So this would be 2 squared times 1/2. And I'm going to go ahead and move over this 10. So that would be 10 times 2 squared times 1/2 is equal to dy dt. So 2 squared is 4. 4 times 10 is 40. Times 1/2 is 20. So this would be 20 is equal to dy dt. And specifically, let's see, our measurement of distance is kilometers and our measurement of time is minutes. So this would be 20 kilometers per minute. And that would be our answer. Okay, so like I said, the key thing for today for this related rates day 2 is just making sure that you're checking before you get going. Is there any constant that I need to plug in for before I take my derivative? And is there any variable you need to eliminate because I don't have enough information before you can take our derivative? So those are the 2 things you have to check when you're doing related rates problems before you take a derivative. And you'll usually figure it out, because if you take your derivative and then you plug everything in and you're like, oh crap, I don't have this, and now I have 2 or 3 unknowns in the problem, okay, then you can kind of look back on and be like, okay, what's happening? Oh, that's not changing, or oh, I need to eliminate this variable, something like that. Okay, but that is day 2.